We finally made it to the part that most consider the game, the top-down action sequence. We'll design the gameplay across several arcs, starting with the mission map. Then we'll bring in the ships, their actions and interactions. We'll consider AI control before turning our attention to the user interface and wrap up with mission scripting. This video will cover the entire design and will separate the programming across the next several videos. So in our design document, we'll flesh out the idea of a mission. This idea will take about 10 objects and several dozen interactions. But we'll start by asking a simple question. What's in a mission? I think we agree that we start with a world. In our case, it's the city map that the player's ship flies through, fights other ships, and completes the missions. The player also has a heads-up display that maintains useful information for completing the mission. The game wouldn't be challenging if we didn't include an AI. All non-player ships have an AI attached to them. And the mission itself wouldn't be complete without a goal. The player has a purpose in the mission, and we have to enforce that purpose. Now, each of these elements in the chart will take at least one programming video, and AI will take 2. So let's bring out the object model. OBJ map will load and display the world information to include the visual sprites and a collision map. We'll have a camera object whose sole purpose is to manipulate the player view. We'll have a generic ship object that we'll overload to provide all the function of all the ships in the game. Each ship will have a child AI object that passes commands to the ship object. The UI HUD will have a dedicated object to manage visual information. We'll have a headquarters object that functions as a master mission control. And finally, we'll have small single-use objects that provide effects like gunfire and explosions. Now let's talk about the in-game world. Each episode has one or more world map files that we've already dissected. We'll read these files into a 2D array in column major order. Now in GameMaker we use a data structure called a grid. Now as we learned before, these data structures indicate which 32 by 32 sprite to draw in the world in what position. Well, using these sprites we infer a collision map. It's a simple Boolean array that says whether it's passable or not. Once we have the map here in RAM, we have to draw the world. Now let's talk about performance for a minute. Displaying 40,000 sprites in the room every frame is serious business. Now I initially programmed this on a mobile processor and I was only able to pull about 20 FPS doing a direct draw from RAM every frame. Now that's without any other objects in the room. Well, the common way to do this is to store the world in video RAM close to the screen. We'll draw the whole world once and then just rely on the video card to blit the part of the world that we're interested in every frame. Now that may sound like a good thing, but there's a huge trade-off in system resources. The whole world is now using over 150 megs of video RAM, even though the actual game is barely a couple megs by itself. So I just showed you the spectrum of possible solutions, and I think a good design will aim for somewhere in between, but I'm going to keep this last solution for now. Also note in GameMaker, video RAM data structures are called surfaces. Now this is analogous to textures in SDL. There's one more serious consideration. I plan on deploying this prototype in HTML5, but the GameMaker toolchain doesn't support binary reading on a web server. But if we tried to read the map file as text, the system won't return the actual values for some of the ASCII control characters. We'll have to convert the map file to an ASCII or UTF-friendly format before performing text reads. So this is the path we'll follow to a functioning map. Also, when we build the mission room, remember that our map is 201 by 201 at 32 pixels per tile. So we're looking at a room size of 6400 by 6400 after I shave off the edge. Now, if you do the math of 6400 by 6400 at 4 bytes per pixel, that's where I got the estimate for the video RAM usage. That's a 40 megapixel image. Along the way, we'll add some helper functions to make life easier. We'll have one that converts pixel positions to map grid positions. Now, since all of our actual objects will be located in the room by pixel, we'll need to look up collisions on the grid. Then we'll have a function to calculate Manhattan distance. This will be used to calculate our A-star pathfinding algorithm later on. Our map object will do the following tasks. On create, we'll set references, variables, create our data structures to include the drawing surface, and then load the map. Free everything on destroy. Then draw part of the surface as needed. We'll never need to draw the whole world unless we add a feature that allows widening the view. We'll have a camera object that'll respond to the keyboard, at least so we can test. And we'll set references. So on destroy, we'll have to release the keyboard. We'll process commands on step. Also, I'll have the room view locked to the camera object and let the engine itself manage the view. I think that'll do for now. When we program this up, I might demonstrate various drawing and performance trade-offs to illustrate how design decisions impact performance. Let's move on to the ships that both the player and the AI control. Now, the controls we're interested in are the arrow keys for movement. Now remember that movement is absolute. Pushing right makes the ship go right. Pushing another direction makes the ship turn and go in that direction. Spacebar is fire. Tab changes weapons. And I want to add a self-destruct key, if only because there's no way to end the mission otherwise until we're finished development. Some of the variables we'll include with the ship include all the capabilities and statistics, such as ammo, delay timers. Now obviously there's many types of ships. Also, ships will be on different sides, ally, enemy, or neutral. There's a couple of other points I want to write down too. I'm going to process all of the actions using bit flags. This helps us separate out the input processing from the input handling phase, which is pretty important when gameplay has a lot of dynamics where many things could happen. Now, I also want to change things up from what we've been doing in the first few rooms. I'll base the ship statistics on the actual in-game help file. I'll set the speed of the ships on the GameMaker standard unit of 1, which means 1 pixel per frame per update. I may have to have some kind of arbitrary scalar multiple to make sure the game behaves like the original. Now I'm going to handle collisions manually. I'm not going to be using any of the GameMaker object masks. Instead, I'm going to use a remarkably simple 2-point check that simply reverses the direction of the ship. Now this concept is probably only ideal for the traffic department world, where the ship can only travel forward or backward, has no ability to move sideways, and can never collide on more than one side ever. I wouldn't really try this in any other game. Finally, I'll have the motion of the ship drop 5% every frame if it's not in motion. Now I want to spell out the order of events for the ships in a little more detail than the usual update input render. Each ship is created by the headquarters object, but the create event has to run its course before we can set things like the ship type and thus the ship stats. So we'll separate the creation from the initialization. Now these events only happen once. Now the first part of the life cycle loop updates both the timers and the local physics, which is really just the grid position. Now I want to recalculate other target entities. I read the input for all the ships before moving on to handling that input. We're going to affect the speed and direction of the ship and leave the engine to handle the position updates. Then I want to detect collisions with walls. Remember, ships don't collide with each other in this game. Then make the changes to the shields and armor, which includes the death check. Now here the engine updates the actual room position of all the objects. Then we'll draw the ships. This takes us back to the top. Now let's map this chain to actual GameMaker events. So in Create, we'll make the references and the data structures. We'll have several enumerators, and the action one will actually be a bit field, so that means we'll increment the counter by bit shifting instead of adding 1. We'll set all the late initialization variables on room start. All the ships are created before the room starts, but most of them will be inactive, as we'll see later on. On destroy, we'll clean up the data structures and create some of the effects objects. The begin step event is where we process all of the world updates. The step event is where we detect and handle player input. Then we draw. We also include the direction finder, which would normally be part of the HUD, except it's always drawn relative to the ship. That should just about do it for ships. And now on to AI. Every non-player ship will include one. We'll take on 2 approaches to AI. Now, the first is what I'll call passive AI, because there's really not much intelligence to it. We know that each non-player ship comes with a predefined path in the mission files. Well, this AI will blindly follow that path. The headquarters object is responsible for creating all the ships based on the mission files, and it'll also load these paths at the same time. When a ship reaches the end of the path, it gets destroyed. Well, technically inactivated. There's no kill count or no explosion. We'll use this AI for ships on a particular travel route. Usually the player has to destroy them as part of the mission. Now each AI will use the same control mechanism by pushing commands to the ship's command stack, and that ship will interpret these accordingly. Now the other AI we'll use is an active AI. That includes the ability to just follow the path too, but this one does more. The active AI will change into hunt mode whenever a player or another opponent is nearby. We'll use the A-star algorithm to find the best path between the ship and the target. Now our admissible heuristic will be the Manhattan distance, since that works well in a grid world. We'll be programming this manually within GameMaker. Pretty much all the ships with the ability to shoot will use the active AI. Now here's some of the AI modes we'll enumerate within the AI object. Now, as for the object itself, we'll create the data structure supporting the AI and the pathfinding, set the enumerator, and initialize some variables. We'll have some references and late initializers when the room starts. Finally, we'll handle all the AI modes. Let's move on to the user interface, which is really just the heads-up display printed at the bottom of the screen during the mission. We'll grab a screenshot of the HUD and drop it here at the top. So there's 7 widgets on the display that we'll focus on. The left side is a bar that shows the ship's condition in terms of armor and shields. Next we have a direction finder that's really a tally of the relative locations of all enemy and ally ships on the screen. The blue shows where the home base is. We have a missile counter showing the remaining ammo and a backlight that animates the fire delay. There's a graphic for the current weapon. The comlink here is simply an animation that says press F6 if there's an incoming message. Then we have a ticker that passes messages to the player one character at a time. We'll handle all this with one object that'll update these widgets each turn. We'll set the variables and the references. Each step will get the HUD data, handle the ticker animation, and the overall fading of the backlight. Then we'll draw the HUD in 2 steps because GameMaker has 2 separate draw processes for screens that use overlay as a HUD. Most of the widgets will be on the GUI, but the minimap will be another surface that will draw behind the HUD by removing this part of the graphic. Our last part is constructing the missions that will challenge the player. Now, from the player's perspective, each mission appears to be a series of waves. Each wave activates new ships and objectives that are passed by the ticker. When all the objectives are complete, the player can return to base and complete the mission. We use the headquarters object to provide this experience. We'll start by loading all the ships in the game world, but they'll start in an inactive state and are not visible until the appropriate wave. We'll have to associate each ship with a wave during the creation process. Then the headquarters object will activate the ships at the appropriate time. At the beginning of the mission, wave 1 is activated. Now, for the most part, the destruction or inactivation of the final ship in the wave causes the next wave to activate. So every time a ship is destroyed, the headquarters object will check the status of the wave. If all ships are destroyed, it'll activate the next wave. If it's the last wave, we'll allow the player to end the mission by returning to base. We'll associate each of these tasks with a helper function. We'll start by initializing a mission, of which ship creation will be a large part of. Then we'll need a command for wave activation, of which individual ship activation contributes to. Whenever a ship is destroyed or goes inactive, we'll check the wave status to either repeat the wave activation or complete the mission. So the headquarters object will maintain a list of target ships for the player. This will directly affect the direction finder that's printed next to the ship, showing the way to the nearest objective. Room start sets references and late initializers. On begin step, we'll check for updating the mission wave only if a flag was set that a ship had been destroyed. We'll do likewise for the mission ending check, which really only applies to the player trying to return to base. Then we use the object to draw the overlay that makes the player appear to enter the base building. It'll be drawn a layer above the ship. Destroy will free the data structures. Room end will update the overall game stats like the current mission and the kill counts. And that should be it for our whole design. We're turning the corner for the home stretch of our development. Each of these slides will be the focus of a programming video. Next time we'll get the map loaded into the game world.